This recording is being made for Chandra at University of Delaware. In this demo video made with Dragonfly 4.1, we're going to look at how you can compute and measure porosity in a brick sample. These data are collected on a CT lab from Rigaku. We're going to start by loading the reconstruction file, which is in the format of VOX. So I loaded it a few moments ago. It's in my recent files. I'll click Next. The pixel size or image spacing is decoded wrong, or maybe it's encoded wrong in these files. I don't know exactly what it is, but I'm going to enter the value of 250 microns per voxel, and that'll be approximately correct, I think. For doing actual measurements for your scientific analysis, you'll need to input the proper value here. We'll go ahead and hit Finish. It'll load the data set into our workspace. So we have our object over here. I don't know, this is probably a sample identifier. I'm just going to rename this brick image, and just by double clicking and typing a name and hitting enter. So we have here the sample. It's loaded on a support tray, so you can see the patient bed or the patient sample holder there. On my layout, I'm going to choose a 4-view layout. Now I can see the data in 3D and in 2D. I'm going to adjust the brightness and contrast. If I want to adjust it in 2D, I might use the area tool on window leveling. So I can click this button and now I can drag an area and I can optimize contrast for that area. I can click this button or the escape key to return to track mode. If I want to adjust the brightness and contrast in the 3D view, there are a number of ways I can do it. I can adjust it directly here by dragging. That's pretty suitable. So I can use a middle drag to zoom and a left drag to rotate the sample, and then a left and right simultaneous drag to pan the sample back and forth. So here we have the brick sample. Now, if we were trying to do some segmentation on the pores in this sample, there are a few approaches we could take. I'm going to go to the Segment tab. I can go to ROI Tools. If I choose Define Range with this image channel selected, I could choose Lower Otsu, in which case it will try and identify two phases in the histogram. So you see that there's this phase to the left, which represents the air, and this phase to the right with the long tail, which represents the brick matrix. If I were to turn off logarithmic, then you would see it's a very large peak to the left and a smaller peak to the right. So just choosing Lower Otsu gave me this left half of the histogram. If I had reset and chose Upper Otsu, it would give me the right half. So by choosing the lower half, I have all of the air around the outside and the air in the inside, so the pores. So I could add this to a new region of interest and call this pores and surroundings. That's one way of proceeding. Now if I turn off define range, we see we have this. Now this segments the air on the outside and the air on the inside. It may not do the best job, so at least some of these pixels around the pore, that may not be the best solution. So I'm going to hide this. We may revisit this. Now if instead I had turned on define range, I reset and hit Upper Otsu, and I do add to new, this creates a new region of interest, which is our brick ROI. And we see at this point that it includes the rock matrix or the brick matrix, but not the pores themselves. I would like to include these pores in the sample, and I'll show you why in just a minute. If I take this sample and I apply a whole fill operation, so with this ROI selected, if I come over here and I choose to do fill inner areas along the z-axis, then we can see that, by the way, double click, we'll go full screen and back. So we can see here that this ROI has all of these pixels are now filled in. Something I can do is with this ROI that is called brick ROI, I can come over on the ROI tools panel and I can choose this dataset operation to do split at Otsu. This will take the histogram of all of the pixels that are currently colored purple. So not the entire histogram of the image, which includes all this surrounding air, but just the histogram of the pixels colored purple, and it'll split this histogram or this ROI into a foreground and a background. So when I click split, now we see over here background and foreground. So the foreground are going to be the bright pixels, which are the rock matrix, and the background are going to be the pore pixels. And so you can decide if this is a good estimate, if you like it, so it's including some of these pixels, for example, but not the ones at the limit of the resolution. That's probably a pretty good estimate of the porosity. Now, we do see that along the surface, it's picking up some of these pixels and calling that pore space. Now, what I'm going to do here is I'm going to take the brick ROI and I want to shrink it by 1 or 2 pixels along the surface so we can exclude these surface pixels from our analysis. If I take brick ROI and I ask to do something called a 3D erosion, and I'll use a spherical kernel, and I erode, it's going to erase this one set of pixels on the surface. I'll go ahead and erase one more layer of pixels. So now I have this set of pixels that is my brick, all except the very surface set of pixels. And now if I take the brick background, which really is just the pores in brick, I'm going to use this purple ROI as a mask. I'm going to compute the intersection of all the purple and the red, and I'm going to put the results into the red. That is, I wish to remove all of these pixels that do not intersect the purple. And I can do that by selecting this with a click and then a control click here. And I wish to compute the intersection of these using this button, but instead of putting it in a new ROI, I'll just directly overwrite the pores in brick. So when I click intersection, now I have pores in brick, and it's only including pixels that are inside the pink ROI. Now, at this point, I actually already have everything I need to know the porosity as a single scalar value for this sample, which is to say that the brick ROI, if I click on it, notice when I click on an object, I see its properties below. The brick ROI, which is this pink or purple ROI, is labeling some 10.1 million voxels. The pores in brick, in red, is 370,000 voxels. If I click brick ROI and I ask to compare that 10.3 million with the other number by saying pores in brick and click refresh, it can tell you that the porosity is 3.66 volume fraction. So that's the porosity. Now at this point I have this image data structure that we started with and a few different regions of interest. So don't really need any of these. I'm going to get rid of brick foreground, and I'll get rid of my brick ROI. If you want to keep it, you can, but I'm going to delete it for now. And now I just have pores in brick. Now this is a binary region of interest, so every pixel in my space is either labeled red or not red. If I wish to enumerate the different pores and make measurements on them, then I have to go from a binary region of interest, or a binary ROI, to something called a multi-ROI. So if I right-click on this and I ask for something called a connected components analysis, what it will do is it will catalog every set of connected pixels. So for example, this set of pixels in this pore is not connected to these pixels. But these pixels here are in fact connected to this. If I use my mouse wheel and I scroll through to a neighboring slice, I can see that they're connected to a neighboring slice. So this analysis has revealed 19,000, almost 20,000 isolated components. Some of them may only be 1 pixel big. Some of them are multiple pixels big. So everyone is cataloged and identified in this table. If I want to compute measurements on each separate object, I can click this button and I can make measurements, for example, volume or aspect ratio, and I click up OK, and now I have 2 different measurements, volume in cubic microns and aspect ratio for every object in the table. So I have this, and if I wish to color code everything here by volume, I just click volume, and now you see that the biggest ones are colored in red and the smallest ones are in that magenta. Or I could color by aspect ratio, etc. So at this point I have this analysis done. Now I'm going to close this. When you're trying to visualize pores, it's difficult. So pores are normally thought of as transparent, and so you can't see the pores, you just see the solid matrix. So we can look at this image and know where the pores are, but if we try and color code the pores, so if I turn on this multi-ROI and turn on 3D, you don't really see it. If I if I reduce the contrast of my image channel by grabbing this and dragging down, there are the pores. They don't have a whole lot of contrast because you're just color coding transparent pixels. So sometimes people like to look at the pores not as an image channel and not as a multi-ROY, but as something called a surface mesh. And so if I right click on this, we have the option to compute a cubic mesh. So I'll let that compute. As a result, I'll have a new data structure in my workspace. So I'll have the image channel, I'll have a couple of ROIs, and then I'll have this surface mesh. So if I turn on the surface mesh, it's now being rendered, and we see all of the pores. They're easier to see. Even if I turn away the brick image, we can see all of the pores are now colored, are now rendered as this surface mesh. I would just want to emphasize what a surface mesh is. If I select it and I adjust its rendering to outlined, then you can see the mesh is a bunch of polygons. It's a tessellated surface around each of the voxels that make up each one of the pores. Right now it's kind of blocky. I could choose to smooth the mesh, and now it looks a little better. I'll turn this back to solid. Okay, so we have this this rendering of, I'll turn this off. So we have this rendering of the pores, and right now they're actually color coded by this meaningless label index. If I right click on the mesh and I ask for the measurement inspector, then we have this module here, which I'll just drag to undock. Because this mesh was computed from this multi-ROY. Remember, we right-clicked on the multi-ROY and said compute cubic mesh. In this multi-ROY, we had a column in the table for volume and a column in the table for aspect ratio. Because of that, the mesh inherits those properties. So right now, I'm coloring the mesh by this arbitrary value called label, but if I say instead color by volume, then now everything is color-coded by volume, and I can attach an arbitrary lookup table. So if I choose this, then my biggest pores are colored red and my smallest pores are colored blue, or purple as you see here. I could also choose aspect ratio. So I have a very nice rendering of aspect ratio of the pores or volume of the pores. Now, my pore measurement goes from 15 million cubic microns to 331 million cubic microns. If I want this to have a range, if I want to map this color bar onto a more reasonable range, so go from exactly 15 million to, or maybe exactly 0 million to 350 million, I could choose 0 and 350 million. See if I got that right. Let's add one more 0. Did I do something wrong? 3, 5, 0, 1, 2, 3, 1, 2, 3, and 0 on this side. Am I misinterpreting something? Reset one more time. Oh, 330 billion cubic microns. That's my problem. 330, 3, 5, 0, 1, 2, 3, 1, 2, 3, and 1, 2, 3. 3.5. So somehow I missed a couple 0, 0, 0. Enter. Okay, there we are. So now I'm on this range of 0 to whatever I have, 350 billion. Still looks wrong somehow. The point is you can set the scale to be an arbitrary scale. If I just reset everything to the way it was, well, let's make sure I have everything registered. Okay, if I reset everything the way it is, we can see the pores colored by volume, and I want to show you what the rest of this widget does. I can define a window here, and I can say everything inside this window I wish to render as opaque, and everything outside the window I wish to render as maybe transparent. So now I can look at the small pores, or the medium-sized pores, or the big pores. Or I can take everything outside the window and render it as completely transparent. So this is a way of inspecting or looking at the pores. So this is all using the measurement inspector on a mesh object. You could use the measurement inspector on the ROI if you wanted to, but remember the ROI was not a very useful tool for looking at the rendering. So if I tell it to look at the ROI, we could repeat this analysis on the ROI rendering instead. So here we're looking at the volume just like we were in the mesh. So I recommend using the measurement inspector on the mesh. All right, that should give you some tools to work with for doing a rendering and porosity analysis on the pores in brick sample using Dragonfly 4.1. Just email your follow-up questions and have a good day.